4 bonds. Let's talk about electron delocalization. So ignore this complicated looking thing for a second and look at this. I'm comparing the acidity of this alcohol, this OH group, with this carboxylic acid. Both are OHs. Both acidic protons are on oxygen. And so you wouldn't think there'd be that much of a difference, but there sure is. 10 pKa units. That is 10 orders of magnitude different in acidity. So this is a bigger effect than we saw when we looked at the inductive effect. So this isn't just an inductive effect. So what's going on here? Well, first we need to think about this conjugate base and figure out how these electrons are being stabilized. Again, that's what gives us strong acids. Strong acids have stabilized conjugate bases. And this conjugate base is stabilized by resonance. To understand that, we're going to look at its molecular orbitals. So before, we looked at making the pi and pi star orbitals, if you remember. We took 2 p orbitals, we got 2 molecular orbitals out of it, because that is how it works. The number of atomic orbitals gives you the same number of molecular orbitals. So now, instead of starting with 2 atomic orbitals and getting 2 molecular orbitals, I'm really going to start with 3 atomic orbitals and get 3 molecular orbitals. Right? So, or you can think about it as mixing this pi and pi star with one more p orbital, filled p orbital, from this O minus. Okay? So again, 3 atoms, 3 p orbitals, 3 molecular orbitals. So the bottom one and the top one are kind of easy to suss out. The bottom one just has everything mixing in phase. The top one has nodes between all the atoms. Everything is kitty-wumpus, as it were. What's this middle one look like? It looks like this. So here I've got all my electron density on the oxygens. None in the middle. There's actually a node at carbon where there's no electron density. So does this mean that it's kind of jumping from one oxygen to the other? No. What it means is my electron density is smeared out, in this case equally, between these 2 oxygens. Letting electrons spread out makes them more stable, lower in potential energy. Why is that? Because every electron has a negative charge. Here, the charge in this conjugate base is constrained to that oxygen. Right? I've got a lot of electron density in a little bit of space. That'd be like fitting 6 people into one dorm room and saying, live here for a while, right? You get in each other's face, it's not good. Here, we can at least spread them out over 2 rooms, which is a little bit better. All right? So being able to spread out electrons gives us more stable molecules. In this case, we are stabilizing the conjugate base, which makes this a much, much better acid. Again, 10 pKa units better. We'll be talking a lot about resonance in this class, throughout the class. So I don't want to put too much on this today. But for now, we'll just say that we can recognize resonance, in this case, by looking for a lone pair next to a pi bond. Right? And by lone pair, I often mean charge, right? Because our charges, our negative charges, typically come from an extra lone pair on an atom. So let's compare these 2 molecules. This is called cyclohexanol. This is phenol. So very, very similar shapes and structures. OHs on both that we're looking for the acidity. Again, pretty sizable difference in acidity, 5 orders of magnitude. Why is that? Right, let's look at the conjugate base for each of these acids. So these are the conjugate bases of these things. So here, this minus charge is stuck on this oxygen. There's actually a hydrogen on this atom that we usually skip drawing, but it's still there. There's no way for me to, say, push charge onto this carbon because this carbon already has 4 bonds. And as the theme song tells you, carbon takes 4 bonds, not 5. So here, though, I have a lone pair next to a pi bond. Not on the pi bond, but next to it. And so I have this 3-atom chunk. And that's my pattern. That's the pattern I'm looking for. A lone pair next to a pi bond, that 3-atom chunk. When I have that, I can redistribute the electrons to put that lone pair on this carbon. Like that. Those are resonance structures of each other, right? Single, double-headed arrow. These are not different things. These are not flipping back and forth. This is two different ways to draw the same thing, and this is communicating that these electrons in the oxygen are actually spread out into the ring a little bit. Now, if you look at this resonance structure, you can actually see our pattern show up again. Here, I've got a lone pair next to a pi bond. So I can actually draw another resonance structure. So that charge can spread out. It's not equal. Most of the charge will still be on oxygen here. Why? How do I know that? Well, oxygen is a lot more electronegative than carbon. And so given the choice, most of that electron density is going to be on oxygen. But a little bit of it will be on carbon. So comparatively speaking, this conjugate base is more stable than that conjugate base, because this conjugate base is stabilized through resonance. It's able to take that negative charge and kind of smush it out over a larger space. On homework or on an exam, you might be shown one molecule and asked which is the most acidic proton. Remember, whenever we're asked about what's more acidic, we're really being asked what's more stable among these conjugate bases. So here, what we might want to do is think about a couple different potential conjugate bases that we could get to from this thing. So here are three potential conjugate bases. I only got these by taking an H plus from this molecule in different places. So for this one, I took the H plus away from the middle, right? There's an H here that I didn't draw. For this one, I took one of the H's, I guess, down here. And for this one, I took one of the H's on the end here. So we can apply this thinking. We're looking for lone pairs next to pi bonds. That's a stabilizing effect. If I start with this one on the bottom, notice that there isn't a lone pair next to that, right? This isn't part of a 3-atom chunk with a pi bond. I've got this hydrogen here, where if this electron's like, hey, can I make a new double bond there? This carbon would have 5 bonds. Not good. So there's no resonance structure on this one. And so this one is going to be not stabilized, and that's not going to be the most acidic proton. We look at these two. Now, this one on the end, we can see, okay, this one has that 3-atom chunk there. And so I can draw a resonance structure where I delocalize the charge onto that oxygen. Again, resonance structures. Okay, cool. That's going to make it quite a bit more acidic than this one. If I look at this one, though, now you can see that I've actually got 2 pi bonds that I can delocalize that charge into. So I can spread this charge out among both oxygens. I can draw it like this or like that. So in reality, I can kind of think of this big 5-atom chunk and having the charge spread out over the whole thing. So the resonance stabilization is greatest in this conjugate base. It's less in this conjugate base, and there's no stabilization in this conjugate base. So what does that mean for acidity? It means that the most acidic proton in this compound is going to be this H, because if I take that H+, I get to the most stable conjugate base. And so the pK for that one, if you look up in a table, it's about 9. It's pretty acidic for a CH. The pK, if I were to take a proton over here, the pK would be about 20, which is typical. If the rest of this wasn't here, compounds like this, ketones, are typically around 20. Okay? So I will always take this proton first, and if I have a strong enough base, maybe I would take that one second. Okay? This one I would really never take. The pK for these one on the bottom are going to be those really, really big numbers that we saw on like methane, right? 48, something like that. And so there's really no way that I can get a minus charge down here. Okay, so again, when I'm asked what is the most acidic proton, I'm really being asked what's the most stable conjugate base. In this case, this is the most stable conjugate base, and so this is the most acidic proton. So far, I've only shown you resonance when it comes to carbon and oxygen. That's really, really common, really, really important to both synthetic chemistry and biochemistry. But it's not the only game in town. So I just wanted to show you some other cases where we can delocalize charge and make things a little bit more acidic than we'd expect. If you want to stop the tape right here, try to draw the conjugate bases of these compounds along with some resonance structures thereof. Okay, so let's start with this nitro compound, pKa 10. Remember, without that NO2, the pKa would be like 50, 40 to 50. And so this is a huge, huge impact. This is really strongly electron withdrawing. It's sucking electrons into itself. So the resonance structures of the conjugate base would look like this. Of course, nitro groups always have resonance between the two oxygens in that group. It kind of looks like a carboxylic acid, but with a nitrogen in the middle instead of carbon. Again, the orbitals for an NO2 group would look pretty much just like the orbitals for that CO2 group that I drew earlier, where the charge is evenly distributed between the two oxygens. But when I have a negative charge over here, I have yet another avenue for resonance, like this. Again, analogous to the case when this is just a CO double bond going to a CC double bond. So all of these are resonance structures. Obviously, oxygen is pretty electronegative, and so it kind of likes to hold that charge, or it doesn't mind it as much as carbon does. And so this resonance structure in particular helps us understand why this thing is so acidic. Nitriles like this are a little bit less acidic, but they're still acidic enough for us to use synthetically sometimes. Here's the conjugate base of this thing. Now again, our pattern that we're looking for is a 3-atom chunk with a lone pair, and anytime carbon has a negative charge, that's a lone pair. A lone pair next to a pi bond. Lone pair next to pi bond means that I've got resonance stabilization, and I can draw a resonance structure. So notice that in my 3-atom chunk, the charge kind of jumped from 1 to 3, and my double bond moved over 1. Sometimes people use arrows to find their resonance structure. So they would draw an arrow denoting electrons moving, atom to bond, and then another arrow denoting atoms moving bond to atom. I'm not going to stress out about arrow drawing right now. That's going to come up really, really hard in about week 6. And I'll talk a lot about more about arrow pushing at that point. For now, I want you to focus on this 3-atom pattern where I have 3 atoms, lone pair, next to a pi bond. Finally, let's look at a sulfur compound. This is a sulfoxide. That's one of those functional groups that I did not ask you to memorize. So here, the conjugate base would, again, we'd lose a hydrogen on this carbon. And we can draw resonance structures to put that charge up on oxygen, just like we could if this oxygen was a carbon. So this charge is spread out between oxygen and carbon. It's probably hanging out on oxygen most of the time. Oxygen is more electronegative. But it does react like a C- thing at some times. So it's important for us to remember that that charge is spread out between and among these 3 atoms. So to summarize, when we're thinking about acidity, again, we're thinking about the stability of the conjugate base. Conjugate bases can be stabilized by lots of things, but one of the most impactful ways to stabilize charge is to let that charge spread out. And that's what we do when we stabilize by resonance. When I have an extra charge that's next to a pi bond like this, the p orbitals can line up and I can spread that charge across the system. Spreading out the charge makes it more stable, making the conjugate base more stable, makes this acid more acidic.